Hello everyone, welcome to IMS GATE Academy. I am Atul Negi and we have started our foundation course on fluid mechanics, and as you all know we have covered kinematics, okay, statics we have covered, and in the dynamics part we have discussed regarding the Bernoullis theorem, okay, Bernoullis equation we have discussed, Euler's equation, the derivation of the Euler's equation we have done, and previously the Navier-Stokes equation we have also done, and we have seen some numericals also, right? So whatever the topics that are very important for the GATE examination that we are discussing in the foundation course. Okay. So in the dynamics part, now today I will be discussing the application of Bernoullis equation. Okay. So if I talk about the application of Bernoullis equation, but before that you should understand what is Bernoullis equation actually represent. So if I ask you like what actually Bernoullis equation represents, can you tell? Please, if you have attended the last lecture, then you should understand what actually the Bernoullis equation will represent. Most of the time the common mistake is what the students will say, sir, it is a conservation of energy. Okay, so we have discussed it is not a conservation of energy simply, it is a conservation of mechanical energy, in which pressure, static head we have considered, pressure head, kinetic head, and the datum head we have considered. All the summation of these three heads is what constant during the flow in the Bernoullis equation, and we have also seen some assumptions that we have taken while deriving the Bernoullis equation. Okay, I hope all those points is what clear to everyone. Now if I talk about the application part, we will apply this Bernoullis equation in basically some devices like Venturimeter, orifice meter, petard tube, nozzle meter, okay, all those devices. Now first of all I will be discussing the Venturimeter, and I hope if you understand like what is the purpose of Venturimeter, what is the main function of Venturimeter, and in the college also there is one experiment related to Venturimeter also. So what actually we are calculating with the Venturimeter, how Venturimeter helps us in the fluid flow. So what is the function of Venturimeter? Anyone? Please tell me. If anyone knows like what is the function of Venturimeter, so please try to answer. Okay. So what we are going to discuss, the Venturimeter. Now you should understand the purpose of the Venturimeter. Venturimeter is used to calculate the discharge. Venturimeter is used to calculate the discharge of the flowing fluid. Okay. Now as you all know, in the kinematics chapter we have discussed the discharge as what, area into velocity. Okay. Now just by installing the Venturimeter in a pipe I can measure the discharge. Okay. Some values I need, and if I put directly those values in the formula of the discharge, in the case of Venturimeter I will get the discharge value, right? So Venturimeter is usually installed in the pipes to calculate the discharge. Okay, with the help of Venturimeter I used to calculate what, the discharge, and other devices like orifice meter is also a device through which we can calculate the discharge. Okay, so there are some devices. Now we need to understand how this Venturimeter look like and what is the fundamental concept behind the working of Venturimeter. And we should also aware of how the Venturimeter looks like, what are the parts of the Venturimeter, what is the basic configuration of the Venturimeter. All those points it should be clear, right everyone? So we'll start with the Venturimeter, right? Okay. Now, so we will start. First of all, we'll write regarding what it is used to measure the discharge. So this is the point that everyone should remember. It is used to measure the discharge, right? That is the point. So this Venturimeter, now I will show you how it looks like. See, right, now see everyone. Let's suppose this is the pipe. Let's suppose this is your pipe. Okay, and This is the conversion portion that we are having. This is the conversion portion. Okay, everyone. Now see. Okay, everyone. Now see, very important point. So the point that we need to remember here is, let's suppose this is the pipeline we are having, and in the pipeline we have installed a Venturimeter. Venturimeter will have a three parts. This is the conversion portion, this is the small throat portion, then this is the long divergent portion. You need to understand what are the basic parts of the Venturimeter. Okay, so one by one we'll discuss about convergent also, throat also, diverging part also. Okay, so the remaining part, this is your as usual pipe. Okay, in the pipe we have installed this Venturimeter. Okay, everyone, see. Now, so let's suppose this is the diameter D1. Let's suppose the diameter of your pipe is D1. Okay, this is the throat that we have mentioned. Okay, this is the diverging part. This is the converging part. Right, converging part, throat and diverging part. I hope the points are clear. So this is the diameter D1 and also this is the diameter D1 of your pipe. Again, now at the throat, let's suppose the diameter we have assumed D2. At the throat, diameter is D2. So as we have told, like Venturimeter, purpose of Venturimeter is used to measure the discharge. Okay, so in the pipe we have installed this Venturimeter. Now one more thing is there, apart from this convergent, throat and the diverging part, there is a U2 manometer. There is a U2 manometer. See, okay, there is a U2 manometer. Okay, so this is the U2 manometer that I have installed in the pipe also. So this end is on the pipe, another end of the U2 manometer is at the throat. So obviously some fluid flow will be there. Okay, now there is one here as a manometric fluid is also there. A manometric fluid is there here. Okay, everyone, see, try to understand. Let's suppose this is the manometric fluid you are having. Okay, so let's suppose this is the manometric deflection we are having, X. So this is the manometric deflection we will be having now. So as far as the basic construction details of Venturimeters are there, you can understand from this diagram. Converging part, throat and diverging part. Now one by one I will be discussing about each and every part. First converging part, then throat, then the diverging part. But up to now I think the basic diagram is clear to everyone. The basic diagram is clear, yes or no? Please tell me first. Manometric fluid. Clear everyone? So till now all the basic details of the Venturimeter is clear to everyone. Okay. Now, actually what happens in the Venturimeter, try to understand a very important point. With the help of this converging part, what we are trying to do? So obviously some velocity V1 will be there in the pipe, the water which is flowing in the pipe, let's suppose the velocity is V1. Now when it enters into the convergent part, what is happening? The area is reducing. When the area is reducing, what is going to happen? The velocity is going to increase. So because of the change in the velocity in the pipe you will be having, there will be a pressure change, and because of the pressure change I will be able to calculate the discharge. Now you will be thinking, how with the pressure change we are able to calculate the discharge, right? I will show you all those basic mathematics. I will discuss here all the basic concepts, how from the pressure change I can measure the discharge here. So but you should remember, because of the pressure change due to the velocity change, please remember this point, otherwise in the pipe flow the pressure will always change. Correct? Is this point clear? Pressure gradient exists whenever flow is there in the pipe, pressure gradient exists, but when the velocity changes, because of that the pressure changes. So from that pressure change I can calculate the discharge. Now remember this point, because in other devices like orifice meter, nozzle meter also, you will see because of the pressure change, you are able to calculate the discharge. Okay, now we'll discuss the procedure how to calculate the discharge from the pressure change, that we'll discuss. We'll apply the Bernoullis equation obviously, because it is application of Bernoullis equation only, right? So up to this point everyone, this is clear. So with the converging part, the velocity increases, pressure decreases, right? So pressure decrease, and because of that pressure decrease we can calculate the discharge. Till now anything, any doubt? Anyone, please tell me fast. Okay, clear? Now try to understand next point. One by one I will discuss. First I will be discussing the converging part. I will discuss the converging part, right? Now in the converging part, please try to understand. So let's suppose what is going to happen in the converging part, area is decreasing. Area decreases, correct? Area decreases, and as a result of area decreases, what is going to happen? Velocity increases. And increase in velocity, what will happen? What is the effect of increase in velocity? Pressure decreases. I hope this point is clear. As the area decreases, velocity increases from the continuity equation. Okay, from continuity equation I can tell this. From continuity equation, right? And this I can write from Bernoullis equation. From Bernoullis equation. I hope the point is clear, because in the Bernoullis equation you will see the pressure head, the kinetic head, and a datum head. Datum head, because I am assuming the horizontal Venturimeter only, so datum head will be same. So now Bernoullis equation, the two important factors are pressure plus kinetic. The summation of pressure plus kinetic is what? Constant. So as the velocity head or the kinetic head is going to increase, the pressure head is going to decrease, because the summation, the addition of both the terms, both the parameter is constant. So from that I can easily say, as the velocity increasing, the pressure should be what? Decreasing. So this is what the basic point you can understand here. Now during the flow, pressure decreases, that is the favorable pressure gradient. I hope this point is clear. What is favorable pressure gradient? During the flow, if pressure decreases, that is what the favorable pressure gradient, right? So I can tell here, favorable pressure gradient exists. Very important point I can write. Favorable pressure gradient exists. So what is that? Dou P by dou X is less than 0. This is the favorable pressure gradient. I hope this point is clear to everyone. Favorable pressure gradient exists means dou P by dou X is less than 0. Correct? Any doubts? Yes or no? Anyone? Please tell me first. Done? Clear? Okay. So that is for the conversing part. Second is the thought. Okay, thought. Now please remember, in the case of thought, area is minimum. So as the result, velocity will be maximum. Correct? Yes or no? Velocity will be maximum, right? Just see the diagram. Area is minimum at the thought. So when area is minimum, velocity will be maximum according to continuity principle or continuity equation. I can simply tell, right? So these are the points that we have written for the conversing part. Next, we have written for the thought. So apart from the velocity maximum, what are the points that we can understand? What we can understand? Pressure, what is the value of pressure? Maximum, minimum or same? Pressure should be what? Pressure should be minimum. Okay, finally, the next thing is what? Pressure is minimum. This is the point that you should remember. Okay, area minimum, so velocity will be maximum. Pressure will be minimum. Velocity maximum because of continuity principle, right? Continuity equation. This is from the Bernoullis equation. Now, very important point. Whenever during the flow, when the pressure reduces, what actually happen? Please try to remember the point. During the fluid flow, whenever pressure decreases, what are the possible chances? What will happen? Tell me, what will happen if the pressure decreases? If the pressure decreases during the fluid flow, what is going to happen at the throat portion in this case? Tell me everyone. See, the point is, whenever pressure decreases, it should not decrease up to a certain point, because if it is decreasing beyond certain point, the cavitation chances will be there. Cavitation, possibility of cavitation will be there. So we cannot decrease the diameter of a throat beyond a certain limit. Okay, beyond certain limit we cannot decrease the diameter of throat. So what happens if pressure decreases beyond a certain point? The bubble formation is going to start. That will create what? The cavitation. Okay, so just to avoid that particular thing, we will limit the diameter of throat. We will limit the diameter of the throat. Okay, so usually diameter of a throat, you should remember this range also. Dia of a throat varies between 1/3 to 4/3. Just a minute. One by three. Okay, so there is a range from 1/3 to 3/4. So this range 1/3 to 3/4 of the diameter of pipe. Usually this is the range. Okay, so everyone should remember this range also. Okay, 1/3 to 3/4, that is the range, the normal range for the case of diameter of throat. So it is in terms of diameter of pipe. It is in terms of diameter of pipe. But the most general case, most general diameter that we are taking in the case of throat is generally half. Half of what? Diameter of pipe. Okay. So this point you should always remember. So we cannot decrease the value of the diameter of throat because of the possibility of cavitation. So up to certain limit we can decrease, not beyond that. Correct everyone? Correct. Now, so we have discussed regarding the conversing part, we have discussed regarding the throat. Next we will discuss regarding the diverging part. Next, we'll discuss regarding the diverging part. Now, everyone, please see. So, again, we'll see the diagram here first of all. So, in the diverging part, you can understand the area is increasing. Area is what? Increasing. So, as the area increases, velocity decreases. And if velocity increases, what is going to happen? Or velocity decreases, what is going to happen? Because area decrease, from the quantity I can say velocity is going to decrease. Then what is going to happen with the pressure? So that you can tell just from the basics of the Bernoullis equation. Okay. So we'll write it here. Okay. Area increases, and because of this velocity is going to decrease. Now if velocity is going to decrease, what is going to happen with the pressure? That is the main point. Pressure is going to increase. So again, same point. How we have written this point? You can tell from quantity equation. Okay, and this is from Bernoullis equation. Now, so this is what very normal thing. The point is, what is going to happen if the pressure is increasing during the fluid flow? What is the consequence of this particular point? Pressure increases. Tell me everyone, what will be the consequence? So earlier, in the case of converging part, we have written the favorable pressure gradient. Now in this case, pressure is increasing. It is not favorable. Right, during the fluid flow, if the pressure is increasing, so that pressure change is not favorable at all. Tell me, what is going to happen? What is going to happen if the pressure increases? So in this case, adverse pressure gradient exists. That is dou P by dou X is greater than 0. Now what is the effect of this one? Okay, that is clear. Okay, during the fluid flow pressure increases, that is understood. But what is going to happen with this case? What is the consequence? Tell me everyone, think about it. What is the consequence of adverse pressure gradient during the fluid flow? Tell me the consequence. Consequence, what is the consequence? Flow separation. Flow separation you will observe, right? Flow separation is the point. Consequence is flow separation. Okay, and because of this flow separation, losses you will see in the fluid flow. So consequence of adverse pressure gradient is the flow separation, right everyone? So now basic understanding is clear now regarding the converging part also, thought also, diverging part also. Now if you just look at the diagram, you will observe the length of diverging part is much greater than as compared to the length of converging part. But why? What is the reason? Why the length of diverging part is much more as compared to converging part? Can you tell me? What are the reasons because of which we have kept the length of diverging part as what? More in comparison to diverging part? Please tell me. Okay. So note point, we'll mention a note point here. Length of diverging part is more as compared to length of converging part. Okay, everyone, I hope the point is clear. Right? Okay. So very important point. Length of diverging part is more as compared to length of diverging part. But question is why? Why? Tell me. What are the reasons? What are the reasons? Now, forget about the reason. Now, we'll understand if we keep the length of the diverging part as small, what is going to happen? Now, we'll discuss like that. So, let's suppose a rough diagram I am drawing here. So, converging part, small throat you will see. Now, let's suppose small length of diverging part we have kept. This is the case. Another case, converging part, throat, and the long part we have kept for the diverging. So, length of the diverging part is what? More. But in this case, length of the diverging part is not that much more. So, usually what is going to happen? Now, try to understand a very, very important point. So, in the converging part, acceleration will be there. Okay, fluid will accelerate, velocities are going to increase. Okay, velocities are going to increase. Now, as the velocities are increasing and when it passes through the throat, after that, what is going to happen? Retardation. Retardation is going to happen. Now, if that retardation is to take place for a small length of pipe, and in this case, if that retardation is taking place in a more length, so what is the difference? Because as the velocities are very high, most of the fluid will move like this. So what is this? Most of the fluid will flow like this. It means it will there will be what? A flow separation. Fluid will not be able to remain in contact with the pipe boundary during the retardation, during the diverging part, when it is flowing through the diverging part. If the divergence or the retardation is to take place, the retardation is to take place for a small length, most of the fluid will move like this only. So flow separation, or it will not able to remain in contact with the pipe. And what is going to happen after that? After that, you will see the flow circulation, eddies formation. Okay, eddies or the flow circulation, eddies formation you will see, because finally here the pressure is what? More. Initially here the pressure is less and here pressure is what? More. So finally the reverse flow you will see, the eddies formation or the circulation you will see here, and because of that losses you will see, Are you getting my point? So if the divergence or the retardation is to take place for a small length of pipe, most of the fluid will flow like this, that I've mentioned with the yellow color, and here the pressure is what? More. At this point pressure is what? More as compared to the throat pressure. So reverse flow started. Basically means the eddies formation, circulations start, and because of that losses are going to happen. Because of that losses will be there. I hope this point is clear, everyone. Any doubt? So please ask me. Okay. So flowing fluid will not be able to remain in contact with the pipe if the divergence length is what? Very less. But if I provide the large length of the diverging part, fluid will be able to remain in contact with the pipe boundary. Okay. Now in this case also the fluid acceleration is there. Now when the fluid will move, it will move like this. So obviously in this case also some eddies formation will also be there, but not that much that you can see in the case of the less length of diverging part. That is the point that you need to remember. Very, very important, and in the interviews also most of the time they will be asking this thing. So they will ask what will actually happen if we provide a less length of diverging part. So point number 1, you can say if the length of the diverging part is less, so fluid will not be able to remain in contact with the pipe boundary. So then what will happen? What will happen after because of that? So because of that, you know that after some point the pressure is going to increase, because at the throat pressure is minimum, right? We have written this point also. Pressure is minimum, but as you move forward in the diverging part, pressure increases. So when the pressure is going to increase here, the reverse flow you will observe. Reverse flow, eddies formation, circulation, more eddies formation you will see, more losses, more flow separation will be there. Flow separation is also there, but the flow separation is less as compared to this one. I hope this point is clear, because in the interviews, these are the details they are asking. So you should be aware of like why the length is more, what actually happen if the length is less. All those points, it should be crystal clear. Any doubts, please ask me, guys, if there is any doubt. So remember the pressure here, so let's suppose the pressure of diverging part and the pressure at the throat. So you should understand pressure at diverging part is more as compared to pressure at throat. So reverse flow started because of that. Correct? Yes or no? Correct, na? Okay. So apart from that also, they will be asking the angles. Angle of the converging portion, angle of the diverging portion, all those constructional details you should understand, right? So we will write here regarding this point. We will mention here. Okay. So we have asked now why it is there. So here we will write more losses, less loss. Got it? So main reason is the flow separation. Eddies formation. Correct? Eddies formation, flow separation, all those points. Yes or no? So just note it down, all those points, guys. Everyone, please note it down. Okay. And here itself we'll write for the convergent part, angle is usually between 20 to 21. To 21 degree. Angle of the converging part, right? This angle. For the diverging part, it is usually 5 to 7 degree. Okay. So this question they can also ask why the angle is less. Same reason. Same reason that we have discussed here. Same reason. Correct? Same reason. You should remember the point. Because if the angle is less, so obviously length will increase. Na? That is what the same thing. If the angle is less for the diverging part, length automatically increases. Okay. So vice versa, both the things will happen, but you should understand the reason. Correct, everyone? So I hope regarding whatever we have discussed, first of all, constructional details, diverging, converging thought, everything we have discussed. Any doubts till now? Please ask me. Okay, no doubts. So then we'll move forward here. See. Okay, so just for your reference here, I will show you. This is the pipe. Throat. Okay, like this. Now see. So three regions are there. Okay. So from here to here, area decreases, velocity increases, pressure obviously decreases. Here the pressure is minimum, velocity maximum, like this. And what is going to happen here? Area increases, velocity decreases, pressure increases. So this basic detail you should understand. Correct. Now next, Now we will derive the formula for the Venturimeter. Okay. Now see. Again, just I will draw the diagrams for your reference. Okay. Now try to understand, very important point. So what we have attached here, we have attached the YouTube manometer here. Okay. Okay. We will attach the YouTube manometer. Correct. Now this is the YouTube manometer we are having. Now see. So manometric fluid I will show here. Let's suppose this manometric deflection is represented by x. Correct. Now see. This is the section 1, let's suppose. This is the section 1. So center of a pipe I will take here as a point 1. Center of pipe I will take as a point number 1. Okay, now see. Okay. So point 1 I am taking at the center of the pipe, and here I will take point number 2. Both are at same horizontal level. Remember this point. Both are at same horizontal level. So I can apply Bernoullis equation. Applying Bernoullis equation between 1 and 2. Between 1 and 2, if I apply the Bernoullis equation, now what is going to happen, that I will discuss here. So pressure at 1, let's suppose pressure at 1 is P1, assuming that pressure at point 1 is P1. Simple. Pressure P1 divided by specific weight of the fluid which is flowing in the pipe plus V1 square by 2G plus Z1. Okay. P2 divided by specific weight of fluid plus V2 square by 2G plus Z2. Now both are at the same horizontal level, so Z1, Z2 will get cancelled out, right? Very simple. It will get cancelled out. Now second point. After this, what I will write here, see. Finally, I will be having P1 divided by specific weight plus V1 square 2G, and here also P2 divided by specific weight plus V2 square by 2G. Correct? Okay. Now next thing, if I just simplify the equation, it will look like this. Okay, it is V2 square minus V1 square by 2G. Correct? See. So V1 goes to the right side and P2 by specific weight comes to the left side. So now this point can be written as like this. P2 square minus V1 square by 2G. So what actually this H represents? H is the pressure head difference. So this pressure head difference is there in the Venturimeter because of the conversion portion. Okay. So that's why the pressure changes, because of this velocity changes. Otherwise the pressure will also change. See, during the fluid flow, pressure changes, but this pressure changes because of the velocity changes. And how the velocity changes? Because of the Venturimeter itself. So this is the pressure head difference, P1 minus P2 divided by specific weight, that we can represent with H value also. Correct. Now I will utilize the manometric principle here. How? See, this is the U2 manometer. A reference I can take like this. Let's suppose this is the XX, this is my reference, right? Now try to understand a very important point. Let's suppose from here to here the distance is y. Okay, from here to here the center of the pipe is having a distance y from the reference axis xx. Okay, so from the center of the pipe this distance is what? Y. Simple. Yeah, hi. So this distance is y. Now what I'm using a manometric principle. Please remember what I will do. I will equate the pressure along the xx reference. So how I've selected the xx reference? 2 points we need to ensure. Fluid should be same and at the horizontal level. Horizontal level and the fluid should be same. So that's why the pressure on this point and this point will remain same. Now in order to calculate the pressure at this point will be what? The pressure P1 plus this much head of the fluid, and pressure at this point is this much head of manometric fluid plus this much head of the fluid. Simple, right? So how I will write here? See, after this I will apply the manometric principle. So from manometric principle I will write here first of all. From manometric principle. See, from manometric principle, how I will write the equation? Pressure at this point will be what? P1 plus this much head of the fluid. What is the head? Y. Okay, so how I will write? Pressure P1 plus rho G. Okay, rho G of fluid which is flowing here into distance. Distance is what? Y. So this is the left side pressure. Again, I am showing here this pressure at this point. Pressure at this point is the head of this fluid plus the pressure at point 1. So P1 plus this much head of fluid. Correct. So P1 plus rho G Y. Now about this point, this much head of manometric fluid and this much head of the fluid which is flowing in the pipe itself. So this much head will be what? Total is Y. If I subtract X from the Y, I will get Y minus X of the fluid which is flowing in the pipe, and this is what? The Y minus X of the fluid head. Okay, so here I will be writing first of all the manometric fluid head, rho G M I will write here, into X plus rho G of the fluid into Y minus X plus pressure P2. Correct. Now please remember, now P1 minus P2, from this equation I will be able to get P1 minus P2 which is equals to what? See, this term will get cancelled out from this one. So what are the remaining terms? Manometric fluid minus rho G of the fluid which is flowing in the pipe into X. So X is what common here, I can easily take here. So what is there in the brackets? Rho G of manometric fluid minus rho G of fluid. Now, if I divide the whole equation with the rho G of fluid that is flowing in the pipe, so what I will be getting? See, whole equation I am dividing with rho G of the fluid. See, X, and here it will be like this. Because G will get cancelled out, so rho M divided by rho F minus 1, like this. Yes or no? Tell me guys. And previously what we have written? P1 minus P2 divided by specific weight of the fluid. Specific weight of the fluid is nothing but the density into G only. Okay, I can write it like this also, na? Correct, I can write it like this also. Now, secondly, so we have found out the formula actually. This is what the pressure head difference. So next I will write here. Okay, so this is the formula that we need to remember. This is the formula, right everyone? Here we should understand few points regarding what is X. It is the manometric difference. Or manometric deflection. Better to write manometric deflection. Pressure head difference. Pressure head difference. Manometric deflection, pressure head difference. Okay. Now, most of the time they will not give you directly density. Instead of giving density, they can give the specific gravity also. So if I have to write, see, this much basics you should understand, because properties of fluid already we have discussed, right? So density of manometric fluid divided by density of this fluid can also be written as specific gravity of manometric fluid divided by specific gravity of the fluid, or we can directly write specific weight of the manometric fluid divided by the specific weight of the fluid. So this is what the basic part, okay, everyone should know. Just check your internet connectivity, because from here everything is smooth, right? Just check your internet connectivity, because it is not buffering from this side, because all the internet connectivity is good here only. Okay, don't worry. If any part is remaining, or let's suppose any part you have any doubts, you can ask me. So manometric principle, we have found out this particular formula, very important in the Venturimeter. Just they will give you the manometric deflection. With the manometric deflection, I will be able to get the pressure head difference. I will be able to get the pressure head difference. Just I need to take what? This reading. The manometric deflection is what required to calculate the pressure head difference. Now from the pressure head difference, I will be able to calculate the discharge also. How? See. So as you all know, we have written H equals to this V2 square minus V1 square by 2G. This is the formula earlier we have written. Now, very important point. See, how I can write V2, because as you all know, discharge can be written as area into velocity. So, area A1, V1, A2, V2 I can write. Okay, I can write like this, correct? Now, I will replace the velocity in terms of discharge, so that my formula will be in terms of discharge and I can easily calculate the discharge also. So, I will be putting the values of V2, V1 in terms of discharge. Okay, see how I will put. This is the H value. H value stands for pressure head difference. Now, instead of writing V2, I will be writing Q square divided by A2 square minus Q square divided by A1 square. So this is V2 square, this is V1 square divided by 2G. Now, see. So just multiply this one, you will be having 2G into H. But remember, what is pressure head difference? What is the meaning of H? H meaning is pressure head difference. Now Q square I will take common here. What are the remaining values? 1 by A2 square minus 1 by A1 square. Take the LCM. Okay. Just take the LCM and you can calculate the discharge like this. Okay, so it will be like this. A1, A2 under root A1 square minus A2 square into root 2GH. Correct. So what I have taken the LCM. So a1 square minus a2 square in the numerator part, in the denominator a2 and a1 whole square. a1 square into a2 square, like that. So when under root you take on both the sides, that's why the q square becomes the q. So a1 a2, because earlier it was a1 square a2 square. Okay. So a1 a2 it will be there, and this one a1 minus a2 square becomes under root. It will come under root. Okay, square root. So root 2gh, because 2gh is there. So this is the final formula that we are having. But the important point that you should remember here is this discharge is the theoretical discharge, because we have never assumed in our analysis the losses. This is the theoretical discharge we are getting. Okay, this is the theoretical discharge. So I will mention here TH. Theoretical discharge. Now what is the actual discharge? For the actual discharge, I will be using some coefficient of discharge term. Okay, coefficient of discharge. A very important point here. We'll write it in the next page. Coefficient of discharge, C. It is written as CD. It is the actual discharge divided by theoretical discharge. It is the ratio of actual discharge to theoretical discharge. Okay, so this ratio that we need to take in order to calculate the actual discharge. Correct. So generally for Venturimeter, CD value generally lies between 0.97. Okay, 0.97 or 0.98. So how you will use CD here? In order to calculate the actual discharge, you need to multiply CD with the theoretical discharge. For the theoretical discharge, this is the formula. For actual discharge, just multiply the theoretical discharge with CD. That is what the coefficient of discharge. Okay, so your actual discharge formula equals to CD, right? CD multiplied by A1, A2, root 2GH, root A1 square, A2 square, right? Like this. Okay, I hope the point is clear, everyone. Yes or no? So actual discharge, just multiply the coefficient of discharge with this one. Now you will be thinking, sir, how it is practically, how we can calculate this CD value? Because every Venturimeter you will be having with some CD values. When you purchase any Venturimeter, CD value will be given for that. So how you will calculate the CD value for any particular Venturimeter? So see how to calculate actual discharge. It is what very simple. Just calculate the amount of fluid coming out of the pipe, take it in a container, take the volume, whatever the volume you are having, and take the time under which that volume has been collected in your bucket. So time, let's suppose 5 minutes, this much volume. Just divide that, you will get the volume flow rate. For per second, how much volume flow rate you are getting. So very much simple, like how to calculate CD. Again, this is practical question. In one of the interviews, the examiner is asked like how to calculate CD value. He has told, sir, that CD value is given by the company who is producing that Venturimeter. But how they are actually calculating CD? That is the point. So simply, so from this pipe, let's suppose some Venturimeter you have installed. Okay. So what you will do, that is what the practical experiment we are doing in our engineering also. In the fluid mechanics lab, there is one experiment to calculate the value of CD. Okay. So what we'll do here, whatever the amount of fluid is coming, we will collect it in a bucket. In a bucket we will collect. So let's suppose we have started at time t equals to, at any time, at time t equals to 0. And after time t equals to, let's suppose 5 minutes, we have measured some amount of volume which has been collected in the bucket. So at time t0, there is no volume which is coming out of the pipe. Now we have started our stopwatch at time t equals to 0, and we have taken the total volume till the time is what, 5 minutes. So during that 5 minutes, how much volume has been collected in the bucket? So let's suppose it is 10 meter cube, for example, 10 meter cube. in 5 minutes. So now from this you can easily calculate na ki in 1 second how much meter cube will be there. If you are able to calculate this one from basic mathematics, you will get the flow rate. Meter cube per second you will be getting. So like that we are getting the actual discharge. Theoretical discharge will get from the formula only. Just put the values, you will get the actual discharge. Take the ratios and do this experiment for 3 to 5 times. You will have some CD values. Take the average of that value. You will have some certain value of CD. You will have a CD value. Correct. So that is how we are able to calculate the CD of any device. Now, okay, I hope this much part is clear. Now, what I am actually asking here, like CD part is clear. Okay, I hope CD part is clear for everyone. Okay, so actual discharge, in order to calculate actual discharge, CD we need to multiply with the theoretical discharge. Okay, now let's suppose losses are considered. In case losses are considered in the Bernoullis equation, so how the Bernoullis equation will look like? See, if losses are considered, okay, and let's suppose they have given the value of loss also HL. So how the Bernoullis equation will change? How the Bernoullis equation will change? Try to understand. So P1 by specific weight plus V1 square by 2G, okay, plus Z1 equals to P2 by specific weight plus V1 square by 2G plus Z2 plus this HL value that I am taking. And remember this point, this HL I am taking in a diverging part, okay, because adverse pressure gradient exists in the diverging part. So more of the losses you will see in the diverging part also. It's not like there will not be any loss in the convergent, but I am not taking it because of the negligible value. Most of the losses or the majority of the losses you will see in the diverging part where the adverse pressure gradient exists, right? So that HL belongs to the losses in the diverging part. Please remember this point also, very important. Losses in diverging part, right? Now just rearrange this equation. Just rearrange the equation that we have written for the Bernoullis equation. So we can write it like this. Right. So P1 minus P2 divided by specific weight is the pressure difference. So I can write like this. H minus HL equals to V2 square minus V1 square by 2G. Now see. So from this, just again replacing, see what I will do here. Again I will replace V2 V1 with the discharge. So finally you will be having this thing. A1 square minus A2 square. Okay, like this. Remember this point. So we have written the value of the discharge here, okay, assuming the losses also, that is we have considered also HL. So what it represents? Actual discharge, not the theoretical one, because we have considered the losses. It will represent the actual discharge. Okay, now one more way to write actual discharge is, taking the value CD. This is the one of the ways. To GH. Correct. Now comparing both the equations, what I can write? Tell me. What I can write? I can write simply here. See, both the values are equal, na? So simply you can write CD equals to Simple. CD equals to CD into root h basically. CD into root h equals to under root h minus HL. And from this, what I will be getting? CD value. CD value you will be getting under root 1 minus HL by H. Correct? Yes or no? Tell me guys. Yes or no? Is this point clear everyone? Correct? So this becomes the formula for you for the CD value. This becomes the formula for you, right? Formula for coefficient of discharge in terms of what? The losses, which is directly given in the question. Sometimes, in some numericals, if you see, HL is directly given in the question and they are asking the CD value. So if you able to remember directly this formula, you can calculate the value of CD also. Correct. So you should remember this relation also, value of CD in terms of HL. HL is the losses taking place in the diverging part, or sometimes they can give the total loss in the Venturimeter also. Total loss in the Venturimeter, like that they can also give. Okay, but in our analysis, whatever analysis I have done, I have taken only the losses in the diverging part because of the adverse pressure gradient, right? So I hope the point is clear. How to calculate the CD value? Actual discharge divided by theoretical actual discharge. Okay. What is the range of this, sir? CD value you are asking, right? So CD value, I hope we have written here somewhere where we have written. Yes, 0.97, 0.97 to 0.98 like that. So it means it is a mostly accurate device. Highly accurate result it will give you. Highly accurate result it is giving. Okay. Now see. So all the formulas I hope you will remember, and this formula. With the help of manometric deflection, I will be able to calculate what the pressure head difference. Very, very important formula, right? You should remember this one. With the help of manometric deflection, I can calculate pressure head difference. And you should remember ratio in terms of density, ratio in terms of specific gravity, ratio in terms of specific weight. So all are what? Equal only. Okay. So this relation I hope you will remember. Apart from that, the analysis that we have done here, for the converging part, area decrease, velocity increase, pressure increase, pressure decrease. So pressure decrease means the favorable pressure gradient, right? This is what very important, and in the interviews they will be asking this point, whether the pressure gradient is favorable or not favorable, adverse, like that they will be asking. So throughout area minimum, okay, velocity maximum, pressure is minimum. And one more point, if the pressure is what minimum, chances of cavitation will be there if it is going beyond a certain limit. So it depends upon fluid to fluid, right? This much range of diameter of throat you should remember. Yes, diverging part angle 5 to 7 degree, and the adverse pressure gradient. Consequence of adverse pressure gradient, flow separation. Very, very important point. Okay, what is the consequence of adverse pressure gradient? Flow separation will be there. And after that, why the length of the diverging part should be what more as compared to the converging part. This point you should remember always. Why the length of diverging part is what more as compared to converging part, or why the angle is less for the diverging part as compared to converging. So like that questions they can frame in the interviews also. So everything we have written, they can also ask like if the angle is what more in the diverging part or the length is what very less in diverging part, what is going to happen? You should simply tell, sir, in such cases the fluid will not be able to remain in contact with the pipe boundary. So as the pressure increases during the flow separation start. Moreover, eddies formation will be there, circulation will be there, and because of that more losses will be there. I hope the point is clear everyone, because we need to understand each and every basic aspect of the Venturimeter, so that if in the interviews or wherever, whatever questions they are framing or they are asking to you, you are able to answer it. Okay, everyone. Right, so we have discussed all the aspects of the Venturimeter, right? And we have derived the formulas also. All the formulas we have derived here. Okay, value of CD also we have derived. And how to calculate the value of CD also, that is the practical that we have done in engineering. There is a separate experiment to calculate the discharge, a coefficient of discharge for a Venturimeters. So in the pipe, in the labs, if you see in the pipes, they have installed a Venturimeter, and the experimenter is like calculate the value of CD. So number of experiments we'll do to calculate the CD value, right? Orifice meter experiment also we have done in the engineering. So like that. So these are the things that we should understand, right? So I hope all the lecture regarding this Venturimeter is clear to you. Next we will discuss regarding the more applications of the Bernoullis equation, right? So if there any doubt or any question you are having, you can put it in the comment box also. I will try to resolve it, and we'll meet you in the next lecture. Okay, thank you so much.